So one of my very favorite things to teach about is the organization of the periodic table. And here's why. My prediction is that most of you guys have seen the periodic table before. Oftentimes it's printed in your school agenda. It's usually on the back cover. So think to yourself for a second. Have you seen this before? And what do you think it is? Right? So here's what the periodic table is. It's all of the elements that are on Earth. We talked about elements when we talked about classifying matter. They're pure substances. They only have one type of atom inside of them. And in the world right now, there's about 118. And those elements are organized on the periodic table of the elements so that people can learn more about them and how they work. Now, do you know how the periodic table is organized? Like, I know you've seen it before, but do you understand how to read it? Odds are that you answered that question no. Now, one of the things that's fun to know about the periodic table is that the periodic table was invented by this guy named Dmitri Mendeleev. Go and Google him. He's actually fascinating to look at. He's got a killer beard. Someday I want Mendeleev's beard. And he wasn't the first person to try to organize the elements. Scientists have known about the elements for a long, long while, and they've been trying to categorize and organize them for a long time. Mendeleev was only one of the people who tried to organize the elements into some kind of logical way. You know that about scientists. They always try to organize things and classify things, right? Go back and think about the organization and classification of animal species that we talked about in previous units. It's what scientists do. Now, all of the scientists before Mendeleev that organized the periodic table would organize them by chemical properties or by physical properties, things that you could see the elements doing. And when elements shared similar chemical and physical properties, well, the scientists would put those elements together, thinking that's how we should organize them. What was different about Mendeleev, though, is that when he organized the elements, he realized that at the time when he was creating the periodic table, or his version of the periodic table, he realized that there was a pattern in the way that elements form, and that by following that pattern, we could predict that there were some elements that we hadn't discovered yet. And not only could we predict that there were some elements that hadn't been discovered, but we could even describe what those elements were probably going to be like. So by spotting a pattern and realizing that there were gaps in the pattern, Mendeleev created a periodic table that included gaps, spots for previously undiscovered elements. And more important than that, not only did he leave gaps saying, I think there should be another element that looks like this, he even described what he believed the missing elements would look like physically and act like chemically. And that led to a revolution in the discovery of new elements. Turned out Mendeleev was right. There is a pattern to the periodic table, and if you understand the pattern, then you can identify potentially new elements that haven't been discovered yet. And so Dimitri's work pushed the discovery of new elements forward at a much more rapid pace than had ever happened before. Now, what the periodic table will tell you, if you look at it carefully, is it's going to tell you a lot about the underlying structure of the atoms in each individual section of the periodic table. So if you know how to read the periodic table, you can learn a lot about an individual atom of an element. It will tell you how that individual atom of an element is structured. But if you understand how to read the periodic table, you will also be able to better understand how individual elements relate to or react to or combine with one another all the way across the periodic table. It's actually a pretty sophisticated organizational strategy, and that's what I want you to learn more about in this video. Now we'll start with the easy stuff. If you look at an individual cell on a periodic table, in its most basic form, it's going to look like this. This is the cell for the element carbon. In the center, you're going to see the chemical symbol for that particular element. So the chemical symbol for carbon is C. And that's right in the middle, so everybody understands that when you're talking about the element carbon, if you want to abbreviate it, you could abbreviate it with that particular symbol. In the top left-hand corner of each cell, you're going to find what's called the atomic number. And the atomic number is really important. The atomic number is the number of protons in the nucleus of one atom of the element you happen to be talking about. So this number in the top left-hand corner of this box tells us that each carbon atom has 6 protons in its nucleus. Now, I know what you're thinking, like, who cares how many protons are in the nucleus of an element or the atom of an element? The answer is everyone should care, because it is what makes an element unique from one another. Carbon is carbon because it has 6 protons. If it didn't have 6 protons in its nucleus, it wouldn't be an atom of carbon. The atomic number indicates the number of protons in the nucleus, and the number of protons in the nucleus is the key to determining the unique identity of an individual atom and figuring out which element it belongs to. So in reality, no number is more important than the atomic number. Now, there's usually one final number included on the periodic table, and that's what we call the atomic mass. It's usually down here below the name of the individual element. And the atomic mass is equal to the average number of neutrons plus the number of protons inside of the nucleus of an atom of an element. So every single atom of carbon, no matter where you find it, has 6 protons. Now, if you remember, the nucleus also has neutrons too, and usually the number of neutrons is roughly equal to the number of protons. They're usually equal to one another, but not always. Remember that neutrons are neutral, which means adding them to the nucleus of an atom is like adding a 0 to a math problem. It doesn't really change the atom at all. So sometimes you might have an atom of carbon that has 6 protons and 7 neutrons. Usually they're equal to each other. So usually an atom will have 6 protons and 6 neutrons. That's not always the case. Sometimes you'll have an atom of carbon that has 6 protons and 7 neutrons, or 6 protons and 8 neutrons. It doesn't change the atom at all. Remember, it's the number of protons that determines the unique identity of an atom. Okay, but sometimes you have an unequal number of neutrons inside of an atom. And so that's what the atomic mass represents. And if you look at carbon's atomic mass, because it's 12.001, you know that sometimes there are more than 6 neutrons inside of the nucleus of an atom of carbon. If there was always 6 neutrons, then that number would be 12, right? 6 protons plus 6 neutrons equals 12. Well, because this number is higher than 12, what that tells us is that every now and then you can find atoms of carbon that have more than 12 neutrons. Okay? And we call this number the atomic mass. But remember, of all of these things, the number that matters the most is the one that's in the top left-hand corner. That's the atomic number. It's the number of protons, and it determines the unique identity of each individual atom. Just as a really quick reminder to you, here's a diagram of an atom again. We oftentimes draw the diagram of an atom with really rigid electron shells around the outside edge. It's not necessarily the case. They don't really exist in these perfect round circles, right? What really happens is there's a cloud of electrons moving unpredictably around the outside of an atom. However, this makes it easier to understand how electrons work. And electrons work in a really interesting way. If you think about these electron shells, the very first shell, the one that's closest to the nucleus, always holds 2 electrons. That's all it can hold is 2 electrons. When there are 2 electrons in the inside shell, we say that that inside shell is full. Can't hold any more electrons. And if there's more than 2 electrons in the atom, of a particular element, then it gets another electron shell. And you can see that here. So carbon has 1, 2, 3, 4, 5, 6 electrons. Well, 2 of them will be in the inside shell. And then electrons, or an atom of carbon is going to have a second electron shell. It's going to push the remaining electrons into an outer shell. Okay? And that's really important to understand. We call these electrons that are on the outside, we call those valence electrons. Okay? The outermost electrons are called valence electrons. And that becomes really important later on in this lesson when we talk about how atoms will combine together with other atoms. So remember that term, valence electrons. Now, why does it matter? Or how do they form? Well, the answer is if you have 6 electrons, 2 will be on the inside shell, and the remaining 4 will be pushed into a second shell. Because that inside shell can only hold 2 electrons. You guys get that? Every now and then you will see that represented on a periodic table of the elements. And where they put that is usually in the top right-hand corner. They show you the electron shells up here. So when you're talking about carbon, which has 6 electrons, 2 are going to be on the inside shell, 4 are going to be on a second shell, and if you add those together, you see that you have a grand total of 6 electrons. Now, I hope you've seen a pattern there. Carbon has 6 protons, and it also has 6 electrons. And most of the time, it has 6 neutrons, although not all the time. So do you guys see that pattern? I think that's really interesting to see, and I'm sure it was a pattern that Dmitri Mendeleev discovered when he was first looking at atoms too. Now, I like the traditional drawing of the periodic table, right? Like, I like what a traditional cell looks like with the atomic number in the top left and the number of electron shells in the top right. Like, I think that makes sense to me. However, there's another way that the individual elements on a periodic table are sometimes drawn that I like even better. They're called Lewis dot diagrams, and they look like this. Notice a lot of the exact same elements are there. You've got carbon, the chemical symbol here in the middle, so that C tells us it's carbon. Top left, there's your atomic number again. That's the number of protons in the nucleus. But notice that in this case, there are some dots drawn around the chemical symbol for the C. Those dots resemble the number of valence electrons, so the number of electrons in the outermost shell. And what I like about Lewis dot diagrams is that you can really quickly see, oh, okay, carbon has 4 electrons in its outermost shell. That's going to become really important when we start talking later on about how elements join together into compounds. So by adding this to the periodic table, by using Lewis dot diagrams, you're giving people a really important piece of information that they're going to need later on when they're trying to understand how individual elements combine together to make compounds by looking at the periodic table. Okay, so that's something I like even better. Now, just as a quick review, here is a simple slide that shows you both a diagram of a helium atom and shows you both the Lewis dot diagram for a helium atom and shows you the more traditional view of a helium atom, right? So helium starts with its abbreviation in the middle. That's capital H, lowercase e. Top left-hand corner is the atomic number. That's the number of protons in a nucleus of helium. You've got the atomic mass down here. That is the average number of protons and neutrons added together. Your Lewis dot diagram shows you really quickly that there are 2 valence electrons. That means that helium has 2 electrons. They fill one shell that revolves around the nucleus of a particular atom. And there they are. By the way, don't forget that when you have electron shells, that very first shell holds 2 electrons. So this is a full outer shell. That's going to be important for understanding later too. All right, now I want to show you a couple of elements on the periodic table, and I want to show you a video of how they react when we place them into water. And I'm going to do it right here on my screen. If you have trouble seeing it, remember that you can go to the slides yourself and you can make this jumbo view so that you can see it easier. But I will show it to you here. Now, the two elements we're going to look at first are sodium and potassium. Notice that they're stacked on top of each other in the very first column of the periodic table. Do you guys see that? Okay, so there's sodium and there's potassium. And these videos show sodium and potassium being dropped into water. Now, I do want to remind you right here in advance, don't ever drop sodium or potassium into water. They're incredibly dangerous chemical experiments, but somebody else has done a video for us, so let's go ahead and watch it. Does that make sense? Don't do this at home. However, you can watch it here because somebody else has done it under very safe conditions. Let me go and show these to you. Here's sodium in water. See it burbling around the top and moving in really rapid patterns, sort of biffing off the side of the beaker? Right? That's how sodium reacts when you put it in water. Now let's take a look at potassium. Potassium is directly underneath sodium on the periodic table. Let's see how it reacts when you add it to water. Again, reminder, super dangerous, don't do it at home. But it's pretty similar, isn't it? It's ripping along the top of the water, it's biffing off the sides of the container, it's moving pretty fast. I would say the only real difference that we see is potassium has some flames that come off of it that sodium didn't. Now, let's look at calcium. Notice that calcium is not in the same column as sodium and potassium. Notice that calcium is in the column right next to it. Do you see that? Let's watch how it reacts when we put it into water. And again, super dangerous, don't do this at home. Now talk about an incredibly different reaction, right? There's no rapid movement. I see no biffing and bouncing off the sides of the container. I see no flame. We've got some bubbling that starts at the very end, but if you look, that's 90 seconds later. That was interesting, wasn't it? I mean, look at the periodic table. Those elements are grouped very closely together, and yet they react differently when you put them in water. These two guys, sodium and potassium, reacted similarly, very fast, biffing off the sides of the container. Calcium, which is right next door, reacted very differently. It moved slow. There was no rapid movement, no flame or fire. Well, that's something that is super important to know about the periodic table. Not only are the elements sort of laid out on the periodic table in a pattern by their physical properties, by what they look like with one another, the periodic table is also laid out so that you can understand which elements are going to react in similar ways under similar circumstances. Let me show you what I mean by that. On a periodic table, the columns are called groups. And all of the atoms, or all of the elements that are inside of a group, they react chemically the same way for the most part. So these elements, they all share some physical properties. In fact, these guys are called the noble gases, and they're all gases in common constant conditions. However, they also share similar reactive properties too. They're going to react in certain ways. And by the way, that reaction is caused by the number of valence electrons they have. When you have the same number of valence electrons, you're more likely to react chemically in the same way to things. For example, these guys are called the noble gases, and they actually have 8 valence electrons. They have 8 electrons in that outermost shell. And that means they don't react with anybody. They like to just exist on their own. So that's cool, right? The periodic table isn't just sorted by like what color are the elements. Periodic table is also sorted in a way where you can determine that individual elements are going to react in the same way based on where they're placed. And what's that pattern? Well, all of the elements that are in a column together will react in similar ways chemically. You guys see sodium right here, and you see potassium right here? Well, they're in the same column. They're going to react in similar ways. You see calcium over here? It's in a different column, so it won't react in the same way that sodium and potassium do. However, it will react in the same way that magnesium does. If I had a video of magnesium in water, it would look a lot like the way that calcium reacted in water. That's cool, isn't it? So by looking at the columns, you can find elements that are going to react in similar ways, have similar chemical reactions. That's worth knowing. Now, a period on a periodic table is called a row. You know, what we call a row on a periodic table is called a period. And from left to right, what you'll see is your atomic number increases by 1. If you pull up a periodic table, you'll see that lithium has an atomic number of 3, and beryllium has an atomic number of 4. Boron has an atomic number of 5. Carbon has an atomic number of 6. Remember, that's the number of protons that you're going to find in a nucleus of an atom of an individual element. Nitrogen has 7 protons inside of its nucleus. Also remember that atomic number is what makes an element unique. So nitrogen is nitrogen because it has 7 protons inside of its nucleus. Well, on the periodic table, one of the organizational patterns that you'll see is the atomic number, the number of protons in an atom of an element, increases by 1 from left to right. That's a pattern that was discovered by Dmitri Mendeleev. The other thing that increases from left to right most of the time is each individual element from left to right increases in atomic number or increases in valence electrons by 1. So these guys over here have, generally speaking, 1 valence electron. That's the electrons in the outer shell. These guys here have 2 valence electrons. These guys over here have 3 valence electrons. These guys have 4 valence electrons. And that's a general pattern. It doesn't work across the entire periodic table, but it does work for the most common elements on Earth. So do you see how that organization works? If you know that an element is in a column with other elements, they're going to share similar physical and chemical properties. We call those groups. And if you know that from left to right, you increase in valence electrons and you increase in atomic number, then you understand that from left to right, those elements and atoms are changing. They're different from one another, from side to side. And we call those periods on the periodic table. I think that's really cool. I bet you didn't know that before. Okay, now the last thing you need to know about the organization of the periodic table is that there are several groups of elements that are bundled together on the periodic table. And those groups of elements are bundled together because they react in similar ways, they form compounds in similar ways, they also share similar physical properties. Now, if you look at the periodic table and I color code it for you, you can see those different groups here. Metals are orange, and it's the largest group of elements that are on Earth. Most of our elements exist in the form of metals. The greens over here, these guys are metalloids. They share properties with one another, chemical and physical properties with one another. Nonmetals are all of the blue things that you see, and then red are the noble gases. So you can see how those things are broken apart. Now, most elements, again, are metals. They melt at very high temperatures. Their shape can be changed easily. Heat and electricity move through them easily. And it's the most important group, or it's the largest group on the periodic table. Nonmetals are obviously different, right? They're not metals. And if you look, they actually have properties that are almost opposite of metals. They don't conduct heat and electricity very well. They melt at very low temperatures. Their shape cannot be changed very well. And that's different from metals, which conduct heat and electricity well, and which also can have their shape changed easily. So, right, you got metals and nonmetals, they have sort of opposite properties of each other. The next group we called metalloids, and they actually have properties of both metals and nonmetals. They can be shiny or dull. Their shape can be easily changed. Heat and electricity will move them through them easily, but not move through them as easily as they move through metals. Okay, so we call them metalloids, and notice that they're positioned in between the metals and the nonmetals, right? So these guys are mostly metals, these guys are nonmetals, and jammed in the middle are metalloids, so elements that act similarly to both metals and nonmetals. Now, my favorite group on the entire periodic table are the noble gases, though. The noble gases are on the far right-hand side, and they don't react with anybody. They share properties with each other. They're all gases. You'll recognize some of them. Do you see neon and helium, right? You know what those gases are. They're kind of cool looking, but they don't combine with anyone else. And that's because they have a full outer electron shell. They actually have 8 electrons in their outer shell most of the time. And 8 is a full number for an outer electron shell. If you have 8 electrons, you don't need to combine with anyone else because you have a full outer shell and you're already happy with that. Okay, so again, there's those 4 main groups of elements, right? You've got the metals. They conduct heat and electricity easily. Their shape can be changed easily. Nonmetals, sort of the opposite. They don't conduct heat or electricity easily. Their shape can't be changed easily. They're very brittle. Metalloids, kind of in the middle. Share some properties with metals and some properties with nonmetals. And then my favorite, the noble gases, far right-hand side. They don't react with anybody. They're kind of doing their own thing over there, which I think is a lot of fun.